Right, let's go to the last of my lectures. You won't be rid of me completely because we have a tutorial this afternoon as well. So we're going to talk about heavy ions mainly, about how you generate them in an event generator. And it will look something like this. I will look at the Glauber formalism, mainly looking at fluctuations that are normally ignored in Glauber formalisms. I will look at the initial state a bit. I will look in the final state, and I will then tell you about heavy ions, how they are implemented in Pythia 8. Talk a bit about what I'm doing right now, which is string interactions. But the main gist of this is heavy ions in Pythia 8, which you will do then in the tutorial this afternoon. Okay. I ended the last lecture by lamenting over the fact that I don't understand heavy ion physics. I do understand it a bit more now, but not completely. Glauber formalism, on the other hand, is very easy to understand. Right? We need to model the geometrical distributions of nucleons in a nuclei. And we need to determine which nucleon in one nuclei interacts with another in the other nuclei, and maybe also how they interact, because that's important, right? So this is fairly easily done. We have the Wood-Saxon's potential that you can fit to basically any nuclei. It has a very simple distribution of centers of nucleons in 3 dimensions, well, 2 in this case, which is basically something over 1 plus an exponentially falling distributions. Where you have the R is the radius of the nucleus. You can have, if you want, a skin width. And you can give it a varying density, but typically the density is assumed to be uniform in the whole nuclei. So basically, for any nucleus with said protons and A nucleons, you generate A nucleon positions by simply having this as a probability density. Now, the parameters in the Wood-Saxons are actually tuned to measurement of the charge distribution. So this is low energy, and we can be, as long as it's a fairly heavy nuclei, we can be pretty certain that we know approximately what we're doing. Normally, we assume some kind of isospin invariance, so we don't care if it's a neutron or a proton, because we're mainly interested in QCD, but of course, we can include them. Just doing like this, there will be no correlations whatsoever between nucleons. And one may wonder what happens if 2 nucleons end up in the same place on top of each other. They shouldn't like that in principle. So what we do is normally to introduce what we call a hard core, basically saying that have a hard core radius of RH, and if the distance between 2 nucleons is less than that, is not allowed. So you can do things like generate a new position for the last one, which is very efficient. But in principle, that will give you a bias somewhere. or you can throw away everything you have generated so far when you have two nucleons on top of each other and start again, which is inefficient and unbiased. This bias can be fixed, and this is done, for instance, what we use in Pythia is the parameterization from the Glissando program, where they have fitted parameters like this with this A needs to be heavier than oxygen, basically. When you get smaller nuclei, you get weird effects. And even in oxygen, you may be sensitive to shell structure, or actually it sometimes looks like 4 alpha particles. So. Okay, so what we can do then, in general, if you have a heavy ion cross section, sigma A of B, then you can get the total cross section by integrating over impact parameter. And the simplest way of doing this is just to say that, well, if they overlap the least, they will interact. If not, they won't. So you can have this as a delta function, sorry, as a Heaviside function, and you get it like that. Now we do these nucleons, generate them, so we can rewrite it in the following way, where we now have a nucleon-nucleon cross section as a function of impact parameter. So this is then the impact parameter between one nucleon in one nuclei and one in the other. You have the densities, and you can get the whole AA cross section saying, well, that's the probability that nothing is done. 1 minus the probability that nothing hits each other, right? So this is the probability of 2 nucleons hitting. 1 minus that is probability that they don't hit. You integrate, and then this will be the probability that nothing happens, and 1 minus that is the probabilities that something happens. It's very easy. But now we need to think about what kind of cross sections we are talking about here. Shall we use the total cross section? Well, it depends on what we're interested in, right? If you have the total cross section here, then you will get all the elastically scattered nucleons that don't really end up in our detector and won't contribute to any particle production in your detector. So you can use the non-diffractive or inelastic cross section and put it there. And this is typically what is done. Now, when I started to look at this, I was interested in fluctuations in these cross sections, because all nucleons are not the same all the time, right? So if you think about the interaction between nuclei or anything, if you have a projectile with some structure in it, the projectile can have different mass eigenstates, of course. So you can expand the mass eigenstates in eigenstates of the diffractive interaction. Call those eigenstate phi k, and these are then the mass eigenstate, where you have the proton will be in the lowest mass eigenstate, right? If you have an elastic amplitude T here, you can then calculate the probability as a function of B for an elastic scattering. That is just same in as out. So you take, that's the amplitude, you square it. And if you look at this, you see that will be a kind of average over the amplitude. And we know that if the amplitude is unity, which is the maximum it can be in this formalism, it's called Gooden-Walker formalism here, then you know that the elastic cross-section is equal to the absorptive cross-section. I will use absorptive and non-diffractive as in the same meaning. And so those will both be the total cross-section divided by 2. And we know this from optics. Remember that Glauber was an optics guy. That the probability of, if you have a black disk shooting photons on it, the total cross-section is all the things that end up in the black disk and it is absorbed, and all the things that get diverted by it, which is then elastic. And we know from that that the elastic is the same as the absorptive. Now, you can then look at the probability of something ending up in another mass eigenstate. So you can look at, you expand these out in interaction eigenstates, and you get the cross-section like this, and you see that it's the amplitude, the average of the amplitude squared compared to this, which was the average amplitude. I'm saying it's wrong, right? The average amplitude squared, the average of the squared amplitude. That's so this. So you soon realize that if you take away, this actually includes the elastic scattering, right? So if you take that away, you will get something that looks like a variance. So the diffractive excitation cross-section depends on the fluctuations in the scattering process, scattering cross-section amplitude. Now, we can assume when we have nucleus-nucleus interactions at high energies, they are two pancakes. And in the iconal approximation, you'd say that their states are frozen during the transition. These pancakes go across each other. We also assume that the elastic nucleon scattering is given by a purely imaginary part of the amplitude, ignoring that there may be a real part of the amplitude. And we can write down these cross-sections that we are interested in. And the fun thing when we do this, dB, so differential impact parameter, this becomes almost like probabilities. Now, you have the absorptive is then twice the total minus all the diffractive, including elastic. And the elastic, as I said before, it's the square of the average, and then the diffractive excitation is the fluctuations there. It becomes a bit more tricky when you have several nucleons in both the target and the projectile are have in a structure. Then you get different averages over the target states and the projectile states. So the probability to have a diffractive excitation of the projectile looks like this. So you see it only depends on the average of the target, not of the projectile. And the same diffractive excitation of the target, looks like that, and double diffraction looks like this. Can be worked out. Now, of particular interest in this connection is the wounded cross-section. So that is the probability that a target or a projectile nucleon breaks up, either through an absorptive or non-diffractive interaction or by a diffractive excitation, single or double. And you can write that down. And again, you see that this only depends on average properties of the target and only on the fluctuations in the proton, projectile. So this is a very simple thing to use, because if you have a proton and an ion, you don't need to worry about the states of the ions, nucleons in the ions. This nucleus, I always stumble on that. You can average over the target ion and only look at the fluctuations of the proton. So the standard way of doing this is in PA or AA. You distribute the nucleons randomly according to Wood-Saxons. You Monte Carlo or random pick the B distributions on each side between the target and projectile, typically with a huge square, because you integrate B over the whole universe. And then you count the number of nucleons that are within a distance D square root of the cross-section divided by pi from any of the projectile nucleons, and you get a number that gives you n col, number of collisions, and n part, the number of participating nucleons. Normally, you don't have any fluctuation there, but you include the diffractively wounded nucleons by using something like this. So you take the absorptive, the double excitation, the diffractive excitation, which is the total minus the elastic. Use that as the cross-section, and that will give you the nucleon collisions that will actually contribute to what happens in your detector. So go away. Yeah. So a more sophisticated way would then be to have fluctuations included. And you can do that by, as was done by Mark Strickman and his collaborators in something they call Glauber-Griebold color fluctuation model. So instead of having a fixed cross-section when you calculate these things, you have a fluctuating cross-section. And they use something like this, Gaussian fluctuations, and then they parameterize the amplitude for the scattering like this. Well, you have the sigma there. And if you think about what that means, especially in PA you have a proton going through a nucleus. Now, if the proton is fixed, there are just that many nucleons you can hit, right? But if the cross-section fluctuates, it can fluctuate up and you can hit much more nucleons. So that's the idea here. Now, counting the number of nucleons and collisions is not all, right? We need to understand better how it works. So what does the actual initial state look like? The fluctuations indicate that there is something going on. And this is my favorite model. It's a little thing called Dipsy. I'll tell you more about it later. And it tells you how the proton evolves in space-time or in impact parameter space as you increase the rapidity or increase the energy of the proton so that you can resolve more things. This is a purely gluonic model. And in the beginning, you have one nucleus here, and each proton or neutron is given as a little gluon, 3 gluon states with 3 dipoles. So this is dipole evolution. And as you accelerate the proton, they start to emitting more gluons in the initial states. And it's formulated in impact parameter space, and so we get more and more stuff, right? And in the end, you accelerate them and they actually collide. What we do here is basically we generate the Fock space, Fock states of each proton. And then when they collide, we freeze all the states and you count the number of dipoles, which dipoles interact with which other dipole. And you say that all other dipoles were just virtual fluctuations, basically. So they disappear. And in the end, you will see all the blue things here are dipoles that has interacted. These ones hasn't. You can see there is a kind of almond shape, but it's certainly not it's a very ugly almond shape. And then afterwards, you will have strings because this is a dipoles. And that's what I said yesterday as well. I want to have strings so I can hadronize them. And here I get strings. There's a lot of strings. But there are other ways of generating the initial state. I think that Thomas have told you a bit about it, or have you? You have, so I can go quickly. So color glass condensate is the dominating thing on the market, which is, it's a mean field statistical approach to this, where you have a renormalization group equation that is called Jimwok or something like that. So it's based on QCD, of course. It's called glass condensate because you get something that looks solid on short time scales. Of course, when you collide them, it's so quickly you don't have anything to work on. And on long time scales, it's amorphous. It's a condensate because there's a lot of gluons. That means we have saturation. And that is important for this. In standard DGLAP, the gluon density increases very rapidly as you go down in X. And the higher energy you have, the lower X you can resolve. Right? That also happens in BFKL, and somewhere it has to stop. And the thing to include is gluon recombination. So this is done here, but in a kind of mean field approach. And the main thing here is that you get some scale, which is very important, the saturation scale, that depends on X. That's the important thing. Yes. And using this is event generator of a kind called the IP glass model, but that uses this saturation, but I think it's DGLAT based rather than BFKL based, but never mind. So that is one way of really looking at the whole initial states to try to figure out what goes on. Another way of doing it is these pomerons I talked to you about. You can basically look at all these things, you do your Glauber calculation, you say who interacts with who, and let them interact with pomerons. You draw pomerons everywhere, and then you cut some, and then you don't cut another, and so on. And each these pomerons would then give either a string or two, spanned by the two colliding nucleons, or by a nucleon and another pomeron. That's one way of doing it. And then the thing I showed you before is this dipole evolution formula, which is then Al Miller, who reformulated the BFKL evolution in impact parameter space. So you have dipoles emitting gluons, creating two dipoles that can radiate further in the initial state. And in the DIPSI program we did for this, we also have saturation, but it's a kind of different kind of saturation, which is very much related to color reconnections that I talked about before. And this really models fluctuations very explicitly. No questions yet. So that was the initial state. You can model this in different ways. When I come to the Pythia model for this, it will be a bit different. And the question, what to do with the final states? Well, there are a lot of dipoles here. I can actually draw the strings, but does that even make sense? We'll discuss that as we go along. One could also just give up and say that this is too much. Let's do thermodynamics. And you notice that I used the word give up. That is, of course, my point of view. It's people like using thermodynamics on this. So, but you can use both. And I'm not going to go through the hydrodynamics because I hope someone has talked to you about it before. Yes. The only problem I have with this is that this thing that happens on some hypersurface where you all of a sudden get hadrons again. I think that is it's a bit of trickery. I don't really understand this. After that, when you have hadrons, you usually have something called hadron rescattering, and that I understand. And that is actually implemented in Pythia. So if it's implemented in Pythia, I understand it. But you have heard about this before, so I will not go through it in much detail. Instead, I will talk about what is implemented in Pythia in this sense, and that is based on the wounded nucleon model. This was a very simple model invented by Biawas and Chish, and which was implemented in the Fritjof event generator, also one of these Lund programs. So the idea here is that you just count the number of wounded nucleons, as we discussed before. And then you say that each wounded nucleon will populate the phase space with hadrons in approximately the same way. So if this is the number of hadrons as a function of eta, you will have something that linearly rises like this. So dn d eta is a simple linear function of eta. And if you have proton-proton collisions, then you have two wounded nucleons. One will populate the space with this much hadrons and the other with that much hadrons, and that explains then why we have a fairly flat distribution of hadrons in a minimum bias proton-proton collision. And then you can go to proton-ion collisions. And here we have, in this case, 3 wounded nucleons. And on the other side, we only have the proton, so we can only have 1. And then you get this tilted spectrum of hadrons that we will see when we look at LHC data later. And then if you go to AA collisions, you again get something which is flat. You basically fit this function to data, and it works very well. It worked too well, because when you implemented it in this Fritjof program, it was really simply modeled by stretching out a string from each wounded nucleus with an invariant mass that reproduced this f of eta. No collective effects, just populating your detector with hadrons. And it worked so well that it delayed the discovery of the quark-gluon plasma quite a bit, in some sense. Now, there are a number of programs on the market, and they all do things slightly differently. So one of the best generators for heavy ion physics is called EPOS, that uses what they call a core corona model. So it starts with this Pomeron picture. Well, it starts with a Glauber calculation, of course, and then connect all the wounded nucleons with a mesh of Pomerons. They create strings by cutting some Pomerons, and then they divide it up. So if the density of strings is locally high, you chop them up in partons and take all those and use relativistic hydrodynamics on them. If there is low enough density, then you allow for hard interactions and perturbative initial final state and MPI evolution, and do normal string fragmentation. Simplicity. So for a low multiplicity PP, there will never be enough string density. In a central AA, there will be a lot, but also in high multiplicity PP, they get into situations where the density of strings is high, and they use hydrodynamics. And it works very well. Another standard heavy ion generator is called Hijing. I would say it's inspired by Fritjof. Hard scatterings using nuclear PDFs, which is good to get the hard scattering correct, including shattering. It actually uses my old program for some of the soft radiation. That's nice. And string fragmentation. So since it's string fragmentation, it's an okay program. That also works very well. We will look at comparison with data a bit later. There is another kind of standard heavy ion generator with more collective effects. It's called AMPT. Same initial state as Hijing, but then it does what it's called string melting. So more or less like it's done in Corona. But here they actually do the string fragmentation and convert the mesons back to QQ bar pairs, which they then evolve in time with elastic scattering between each other. So it's kind of a microscopic way of modeling the quark-gluon plasma. And then they have nearest neighbor recombinations into hadrons and then hadron risk scatterings. That's another one. But what I will talk about most is, of course, the heavy ion model in Pythia, the model we call Angantyr. So what time is it now? Yes. So what are these people? Well, who is Fritjof and who is Angantyr? Well, Fritjof was named Fritjof because other people in Lund had made the Pythia program, and we say, well, we from Lund. I mean, why should we? Pythia is an oracle of Delphi, old Greek things, right? We have a history in Sweden too, and it's the Vikings. And one of the Viking sagas is about Fritjof. So when we started making this new heavy ion, we call it Angantyr. So Angantyr and Fritjof actually knew each other. But the Angantyr was a king of Denmark, actually liked him very much, so he got a lot of power, and Fritjof dwelled unhappily in love with the king's daughter, who, of course, Angantyr stole. And in the end, Angantyr actually killed Fritjof. So with the sword called Tyrfing, so, hence the logo for Angantyr. So we will have a lot of Norse mythology coming up later on as well. So the Angantyr model is this Glauber model with fairly advanced fluctuation treatment. I think it's the only program that actually have fluctuations in both targets and projectile nucleons. It divides the interactions as such into different groups. So not only does it say which of the nucleons interact, we also say whether that interaction is absorptive or non-diffractive, or single elastic excitation, or double diffractive excitation, not elastic. And then it also differentiates between different kinds of absorptive interactions. You have the primary ones, which are modeled just like a Pythia PP. And since we know that Pythia minimum bias PP is the best description we have of data, that is good. Secondary is an interaction which is also absorptive, but one of the nucleons has already been interacting with another. And there we actually model it as a kind of diffractive excitation. I will go into that a bit more later on, with a kind of Fritjof-like thing. And then all the sub-events are generated on parton level, merged into a consistent PA or AA event, and then hadronized with string fragmentation. Although there is no collective effect here yet, but I will talk about what we call string interactions in the end here. So I showed you this before, and it has to do with color reconnections. So in Pythia PP, you don't like to have these kind of situations. If you can, you prefer to reconnect the colors so that it looks color-wise like this, and you get not two cut pomerons here, but only one. So what we do in PA, in Angantyr, is almost the same. You would expect something. So here you now have two different nucleons. And we don't want them to go all the way up to this, but we want to do it that way. But rather than actually connecting it color-wise, we are working on doing that better. We use this uncut pomeron here, which will give you the same kind of final state distribution of hadrons. So remember, this is a kind of half a pomeron diagram. So this is a cut pomeron. And every time you have two pomerons in rapidity here, you get double the number of particles coming out. So it uses the Pythia multi-particle interaction machinery, both for the, shall we say, primary absorptive, but also the secondary absorptive. So here you actually have multiple interactions as well, because this is modeled as a diffractive excitation in Pythia, which for high mass is done by a pomeron proton scattering, where the pomeron is supposed to be a real object with proton densities inside it. And that means you can have multiple scatterings between the pomeron and the proton. And then, of course, if you go to AA and you have two scatterings like this, you have to decide whether you treat this as two completely separate PP events or NN events. Or if you say that, no, well, I first do this one, and then I do this one as a secondary scattering, and then I do that as a secondary scattering, or the other way around. And it's a bit tricky, and a lot of kind of administration to get this working, but it does work. Just to get you a feeling of what it is that happens, we do this Glauber calculations, and we have a simple tritium-tritium collision here. So we have 9 possible nucleon-nucleon interactions, all right? We order them in individual impact parameter. We say that one with the smallest impact parameter are the most important. And then we look in each of the combination, what kind of collision is it? And we get something like this, maybe. So this is absorptive, this is absorptive, this is double diffraction, diffractive excitation of the target, this diffractive excitation of the target, these missed altogether, and diffractive excitation of the projector. So then we go through this list of possible interactions, and we come to the first one, and that's an absorptive. Easy, we send it to Pythia, give us a normal, well, not normal, we tell Pythia which impact parameter to use, because we know the impact parameter, right? Give me a non-diffractive inelastic collision. That's yes, it's this. Then we go to the next one, and then it's these two, and we realize that this guy has already interacted. So this is where we say that this is a secondary absorptive collision, and we modeled that by this target interacting with a pomeron coming up from this guy. So this is a secondary interaction. Next, double diffractive. Sure, then both of these are actually excited, no problem. And then we have this one, which is the diffractive excitation of the target, but no, that has already interacted. So this can't happen. Instead, we go through here, and in this case, all these things, the corresponding projectile or target had already been involved in a way where it couldn't happen. So these 5 wounded nucleons will give rise to 3 subcollisions. So it's quite involved way of trying to get this out. In addition, we sometimes want to look at hard stuff. We want to look at jets, or top production, or Higgs production in heavy ions, or something. And that is done by simply exchanging the hardest sub-event in the collision with corresponding trigger event from Pythia. So if I want W production, I say I want W production, and then when we generate this, the hardest absorptive one, we say to Pythia, well, in fact, give me a W production, and then we reweight things here. And that is something which is important. We get event weights in Angan 2. And you need to take that into account when you do histograms. This is not perfected yet. We are still working on getting the details completely right here. Now, the thing is that when we now do this thing, we, as usual, get more parameters. So we have to think about what to do with them. So we get parameters, of course, for the Glauber, but as I said, that is mainly given by low energy scattering data and fits to that. So that's independent of what we do. The nucleon-nucleon cross-section fluctuations, we can actually fit to proton-proton cross-sections. So again, does not have anything to do with the generation of heavy ions as such. And you will see this when you run Pythia, that it sometimes starts with a fitting for a given energy. It fits these fluctuations to match the total non-diffractive, single and double diffractive, and even elastic and elastic slope parameters for a given center of mass energy. And then we have these secondary absorptive collisions, which we have kind of tweaked the diffractive excitation process in Pythia so that it looks like half a non-diffractive event. So again, this is tuned to stuff that has nothing to do with heavy ions. And then this distribution of the diffractive mass that you generate, which we set to dmx squared over mx squared, like in Fritjof, that could be tuned in. Then that definitely has to do with heavy ions, and we could tune it to PA, but for some reason we never tried to do that. Well, we have tried now, but with just choose epsilon equal to 0. And then there are some other choices concerning energy momentum conservation, which do not have a large impact. So in principle, we can take Pythia, we can look at PA data and try to tune it, whatever we have there. But then going from PA to AA, there are no extra parameters at all. So that is what we like. We like to have parameters, but we want to understand how to determine them. This is what it looks like when compared to data. This is the pseudo-rapidity distribution of charged particles in Atlas for P-lead at 5 TeV. It is divided up in centrality bins. So this is the top 5% of centrality. This is 90 to 95, and so on. And this is very peripheral. So very central, very peripheral. Now, what is peripheral and what is central in this case? Well, it's a bit messy in P-LED, to say the least. You can also think about, I have two different lines for Angantyr here. You can either say that, well, I have my event generator, so I generate the centrality from my event generator, or I can take the centrality observable that the experiment used and just say that this is just cuts on my data. It's fine, we can do that. We can look at this centrality in P-LED. So this is some ET in the forward region in the LED direction. I think it's between 3.5 and 4.7 in pseudo rapidity. And here we can see that it's not a perfect description of Angantyr, but it's not too bad. But depending on whether I used cuts in Angantyr or cuts in data to determine my centrality bidding, I get different answers. But centrality, why is this centrality? Well, you would imagine that it would be sensitive to where the proton is with respect to the, but that is not a very, I mean, it's quite a, shouldn't matter very much where you probe it, as long as you're more or less in the middle. And you realize soon that what drives the centrality here is rather fluctuations. So we have these fluctuating nucleons, and if you don't include it and you have this centrality measure that we had before and count with your Glauber model, which you now don't use to generate events, you just use them to count participants and stuff. If you use a Glauber model without fluctuations, you see that you have something like this. This is if you only look at the impact parameter centrality. So it's very insensitive to the actual impact parameter, as I said. Then you have a plain Glauber. You get these, where you count the number of participants. You have this Glauber-Gribov color fluctuations, two different versions, and you see you can hit many more nucleons. And in the red and blue here is the Angantyr results, and we get even more fluctuations. So when you actually measure this thing here, what determines which event comes here depends on fluctuations, but it also depends on fluctuations in the individual sub-events. Because if you have very large PTs somewhere, it will often spill over here in this some ET, and you can have fewer participants, but the participants you have can have much higher activity. So here we are very much sensitive to fluctuations everywhere. And of course, we must remember that in this case, the centrality has nothing to do with the impact parameter. Nothing at all. And if you would take the impact parameter percentiles that we have in Angantyr and look at the same thing as we did before, you see you get very different results. So centrality is difficult, especially in PA. In P-LED, oh sorry, LED length, on the other hand, there are as much fluctuations, but there are so many nucleons that everything averages out. So here I've actually done the same thing, This is Alice central multiplicity in lead as a function of centrality. And whether or not I calculate the centrality bins from Angantyr or from Atlas centrality determination, that's the same thing I used before, you barely see the difference. Right? This is because all fluctuations are evened out in lead. And this, the blue line here was actually prediction by Angantyr. Not too bad. And this is also the prediction, and this is for xenon. And here you see all these models I've talked about. There's Hyjing, AMPT, EPOS LHC. Don't know what that is. I forgot what that is. And here's this IP Glasma thingy. It's difficult to see, so I zoomed in on the ratio plots. And we have the black line here is Hyjing. They all do fairly well. The kind of brown dotted, red dashed line here is Angantyr, doing quite well. And if you look at the number of participants, again, it doesn't really matter if you do impact parameter bins or not, because here, impact parameter is very well correlated with your centrality measure, which is nice. And you see here the number of participants is a lot. So the thing is, you can easily generate this yourself with Pythia. Just set the beams to this nice thing here. This is the PDG ID code for lead. So you just tell Pythia to use lead. It will realize that, ooh, this is heavy ions. Let's send it to Angantyr to kill it.
This is already the full implementation of the
no, it's in.
It's already contained in the default.
Yeah. You take what you did last week on the tutorial, go in, change the program, and put that in, and you will get heavy ion collisions instead. Right. So the thing with Angantyr is right now, it gives you the no effect of everything what people look for at the LHC. You want to see flow, you want to see jet quenching, you want to see strangeness enhancement and stuff like that, the typical heavy ion signals. You get none of that. So this is a very good tool to see what you can what you would expect in the absence of collective effects. And it's also a very good tool to understand how you do your measurements. And I think one of the more important thing we have done lately is to modify rivets to actually implement typical heavy ion measurements. It's far from complete, but at least there are things there which allows you to do it. And you will see that if you want, you can. I actually told you how to download Rivet. I thought it's may be difficult to follow my instructions there, so will give you better instructions this afternoon. But the fact that there is no, well, let's pause for a while for questions, if there are questions. No. And I go on. The fact that Pithy Angantyr doesn't have any collective effect does not mean that we're not interested in it. So the rest of this lecture, I will just tell you about some of the things that we are looking at. And of course, we will not talk about the quark-gluon plasma. We want to do it our own way. See how far we can go without involving hydrodynamics, but actually having a full microscopic picture of what goes on in the heavy ion collision. So what we do is we look at string fragmentation and we think about what that means. Told you this before, you have the string breakup here with the tunneling out of the vacuum. Exponentially, it should be minus there, of course. And then you have a string stretch between a quark and an anti-quark, possibly via some gluon kinks and so on. And then you chop off hadrons from the ends with this symmetric fragmentation function. And of course, one-dimensional is an approximation. So let's start thinking about what the string really looks like. Because they are not one-dimensional. In fact, we can measure the size of a string with lattice gauge simulations. And you typically get a radius of the string somewhere between 0.25 and 1 Fermi. The lower is done from lattice calculations. The higher comes from, shall we say, bag models and stuff like that. So let's assume R is equal to 0.5 Fermi, just as a nice number, and look at how does a string look like. So we start out at time equals to 0 with a QQ bar pair being produced, say at LEP. They will be very close together. They just interacted. Where is the color field? Well, the color field hasn't had time to expand yet. After a quarter of a Fermi over C, it will have expanded with the speed of light, right? And that means it's actually looking like that, something. You will have a light front going this way, and it will expand this field. And then at T equals half a Fermi, you will reach this size of the string, where the vacuum says, no, you're not allowed to spread any further. So in the future, you will get something like this. And this is what a string looks like. And when you come here, maybe you will have a string breakup and the string breaks. So the string is certainly not a string. It's more like a tube or like a vortex line. Yes?
That radius you're talking about, like the pitch, like the thickness of the
string, yes.
One Fermi is like more or less the radius of the point.
Yes.
That's just
that is what we're up against. Even in the lower here, that are pretty big things, yes. How did I? But everything is a Fermi, right? This is how far the field can spread, and it's natural to think it should be something like a hadron size. Right?
it's not the length of the string.
No, the length of the string is long, right? That can be long. You see, this is half a Fermi, and this is now 2 Fermis or something. This is where the string starts to break up in the middle. And then as you go along, it will break up on other places as well. So we have string interactions is what we're interested in. Since they are big, they will overlap in some way and they will interact. So how can they do that? So we created another little model. It's called Gleipnir. Now, Gleipnir is the thing that ties the Fenris wolf down. the Fenris wolf is a terrible monster. And if you let it go, that means it's the end of the world, basically. So when Ragnarök comes and the world is ending, this is where Fenris wolf will be set free. And the string keeping him in place is made by dwarfs and elves, and it's an extremely durable string. And the only thing that in principle can cut it is this Tyrfing sword. So Gleipnir is the strings, which we will break, right? So the effects we are looking at is the first one, which is related to color reconnection. And that is basically saying that if you have something red going that way and something anti-red going this way, with a possible string in between, if we have anti-red going here and close by here we have a red going there, nature will prefer to have two short strings between them rather than two long ones. In addition, if you have something like this, where this is green and this is anti-green, if you're standing over here, this looks like something blue, right? And if you're standing over here, that looks like something anti-blue. So when you draw a string, you would typically draw it like this. So this is diquark, or it's an actual junction. So basically, there's color all over the place. What we're saying is that you have color screening everywhere as well. And you need to reconfigure these strings, which went all over the place, into something that respects color coherence in some way. Then another thing is that overlapping strings should probably repel each other. So if you have two completely overlapping strings that are parallel, so red, red, blue, blue, anti-red, sorry. If they are completely overlapping, you can calculate their string tension. And in this case, you will find that kappa is actually 2.5, I think, times kappa, let's call it 3. So this will be in a sextet combination. So the total string tension, and that is what we have available when we produce particles to break the string, will be more than twice of what the single string will be. And if we put them far away and they don't interact, then 2 kappa is what we have, right? So again, to minimize energy, you would expect these things to repel each other. They would also, if this was red anti-red, they would attract each other. But we've already taken care of this case when we do the color reconnection, we think. So this repulsion between strings we call shoving for some reason. And that will give us something that could look like a ridge or flow effects. So when it's high density, you like to spread things out, and you would spread things out more in one direction than the other. And then, of course, since we have higher kappa here, that means you get more strange particles, because we had the e to the minus pi mq over kappa. Now, if there is more energy given to you in the release of this thing, you can have relatively more strange quarks here. And that is what we call strangeness enhancement. And the model we have for this is called row patternization. And in fact, I tell you it in opposite time, because we first thought about row patternization, then the shoving, and we're actually not quite done with the color reconnections yet. But, so I will talk about shoving. And that's another peculiarity with strings, is that the momentum is carried by the quarks and gluons. And they are the only ones that carry longitudinal momentum. The string itself doesn't carry any longitudinal momentum. So that means when we have two completely parallel strings, we can only have kind of transverse force between them. And that force looks approximately like that. And the problem here is, of course, that strings are not parallel. You would think that, yeah, in general, all strings goes between more or less parallel to the beam axis when you exchange colors, but that's not true. You get PTs all over the place, especially in Pythia. So how do you calculate something like a transverse little push that is transverse to both string pieces? So we have found, or Gösta Gustafsson realized, that you can have a string situation and a frame where you look at two string pieces, and the string between those pieces will always be parallel in parallel planes. So you can get a push along which is transverse to both of these. And the reason is, since, well, assuming that everything travels at the speed of light, and you start here, and for each time the quarks will travel with the speed of light, and it will always be in a plane perpendicular to the z-axis here. Now, if we then can boost another string piece so that it is, well, not completely in the same plane, so there's a skewed angle like this, then we will have a frame where the strings are always parallel to each other as time evolves. In this case, they're going away from each other, but they could just as well be going towards each other. Drawing 3D pictures is difficult, but if you're going to include momentum as well, it becomes a real mess. So we have a simplified space-time information for all partons. We can transform any pair of string pieces to this parallel frame, calculate and collect small nudges that we add to the primary hadrons, which will then shift both the position and momenta of the hadrons that are produced. And it will give us a ridge. So this is the famous CMS plot from 2009, actually, where they show this near side long range correlation. So red here is normal Pythia, and this is with shoving. And it looks more or less like data. It's not perfect, and we're not happy with it yet. We haven't actually released it inside of Pythia yet, but qualitatively we get a ridge, and we get the right dependence on the multiplicity. So the higher the multiplicity, the more pronounced the ridge, just as they see in the experiment. In heavy ions, it's a bit more difficult. The thing is, we have to calculate these pushes between all pairs of dipoles, and we need to do it many times, and it scales very badly when you go to heavy ion collisions where you can have 10,000s of these small dipoles. So this is looking at the density of strings in kind of not very central, but rather central heavy ion collision. So you see the almond shape, and this is averaged over many, so it's more like an almond shape. And you see that there is a high density in the middle, weaker, and then when you add shoving, it is reduced a bit, and has swelled a bit. Now, this is actually not the density of strings, this is the density of primary hadrons from the string fragmentation in the central rapidity region. But it's a good, it should be proportional to the number of strings. And you can see if you just oppose it, that you get something that looks like flow. So row patternization, I said, if you have two completely parallel strings, you get something, depending on whether the string is parallel or anti-parallel, you can calculate the kappa. This was actually done by Holger Beck-Nielsen in the 70s or 80s, I think. So this is a single string kappa. This is the thing that is 1 GeV per Fermi. And this is then the whole thing. It's easy to calculate. And the relative probability is then for creating a strange quark as opposed to a light quark. You have this kappa effective, which is the energy released when you break the string or the rope. So it's the reduction in string tension that is available to create these quarks. Now, strings are not parallel and not exactly overlapping, but you can calculate an effective overlapness by looking at the electric field. So a string is basically electric flux tube of electric color fields surrounded by currents of magnetic fields. And if you have this skewness between the two strings, they're not parallel, then you get something like this, and this is the distance in Z that we have there. And you can get some estimate on the overlap of these strings. And you can calculate these now, P and Q, whether they're parallel or not, anti-parallel. Sum those up and get, for each string breaking, we can calculate or estimate the kappa available. And it is a bit messy, especially for baryons, because we expect an effect for baryons as well. But baryon production in Pythia is very difficult. And we think we got it wrong 3 times. And we probably have also had it wrong the 4th time. The results are encouraging, but not perfect. If we look at the top here, this is the ratio of kaons to pions as a function of the central multiplicity. Or first divided up in centrality bins, and then here show the average central multiplicity in each centrality bin. And the full lines here are Pythia without any rope effects. And the dashed, dotted, and dashed dotted lines are PP PA and AA for this Gleipner thingy. And you see for kaons, it works fairly well. For proton, no, this is lambdas. It works somewhat. It gives much larger, more lambdas than Pythia, but it kind of is running away here for high centralities. Same thing with Cascade and Omegas. You have the general trend that it increases a bit, but it doesn't flatten out as it looks like in data. Now, we hope, but we're not sure, that this is because we haven't included both effects. The thing is, the interesting thing here is that experimentally, you don't really see anything when you go from PP to PA to AA. You get the same enhancement everywhere. It's like it only depends on the central charge multiplicity, which would sound okay because that means it depends on the number of strings. But on the other hand, looking at the way these events look, and this is now a single event, and where we produce primary hadrons into central rapidity interval in impact parameter. And you can compare for the same approximate multiplicity for PP, PA, and AA. So there are more strings in AA, but they're more spread out. But what gives the actual enhancement here is these little hotspots, which there are approximately the same in both PP, PA, and AA. This is slightly higher. This is a very high multiplicity PP event. And this is even higher, too high to, I didn't find a PP event there. And this is then for the highest multiplicity, this is multiplicity of 1400 particles in the central rapidity bin. And there you see very high kappa effective. Now, the thing that we think or hope maybe can save us from getting this steep increase for high centralities is that if we had been able to switch on shoving here as well, then we would spread it out a bit. Now, unfortunately, shoving and rope hadronization don't work together yet. So we will have to wait and see what happens there. So this is just an illustration how much dilutions we get, and it's not too much. So we can still see how much the dilution is, and this is then kappa effective. And you see going from 5 down to 3.5 something, and spreading out a bit in this highest number of charged particles above 50. And this is also then averaged over many events. So it might work, but we have yet to check it. And of course, this color reconnection we haven't finished yet, and that will also change the picture, especially when it comes to baryon production like this. And then there is also the interplay between shoving and everything, and also with hadronic rescattering. Hadronic rescattering may very well change the flavor composition. And hadronic rescattering is actually implemented in Pythia. And we hope that that will save us from something, because if we look at V2, this flow coefficient in Angantyr with or without this Gleipner shoving effect, this is without any collectivity, and you see shoving does give you more V2, but it's way off from giving you what you find in data. On the other hand, we know that hadronic rescattering will give you V2. So this is, I'm going to default, and this is with hadronic rescattering. And this is a function of multiplicity, so small, high central events here, but central events are here, so turn this around. And we see that the shoving would contribute more in the peripheral regions, actually, while rescattering contributes more in the central region. And I'm counting on that we'll be lucky and they will just compensate each other. We will describe everything perfectly. Okay, that's what I have. As a summary, heavy ion collisions are messy. There's a lot of things, but we have computers that can take care of most of the things. It's not just overlaid nucleon-nucleon collisions, as we do in Nagantur now, and what you will simulate this afternoon. There are much other stuff. There are initial effects that we can take care of in different ways. There are final state effects. There could be a quark-gluon plasma messing things around. Hydrodynamics, string interactions, flow, jet quenching, rescattering, and everything like that. So I will leave this on for a while so you can write down where you should download this tutorial. And in there you will have a PDF, which I will go through when we meet again at 3, with instructions on how to do it. And in the end of those instructions, you will also find more detailed instructions for how to install rivets. And that is optional. You don't have to do it if you don't want to, but it's typically not difficult. We'll see what happens. So while you're looking at that, everybody has taken a photograph, good. A final comment. When I started with this, and when LHC started, the heavy ion and PP communities were quite separate. And this LHC brought them together. And this first interesting result from LHC, that there are collective effects in high multiplicity proton-proton collisions, means that we really had to start talking to each other. And also there are jets in AA, so we need to understand those as well, and we need to learn from each other. And I think we have started to do that, but I think we should talk more to each other. Not quite lunch yet. Should we do an exercise? Exercise for your stomach. I did this once. We organized a conference in Lund called LHCP, it's an LHC physics conference. And I was giving I was kind of the toastmaster of the conference dinner. So we sang Swedish schnapps songs and stuff like that. And I realized that all the cultural things that they got to do was about Christianity. Yeah, I mean, Lund is famous. It's been a center of the Christianization of the Nordic countries since the 11th century or something. But I thought there are something that we need to add as well, right? I mean, the true history of the Norse tradition. So I have a friend who taught me how to galdr. 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 So maybe some of you have seen this Netflix or HBO series called Vikings. You have these female priests, the vulvas. They don't do it properly in the film. When they come and sing, it's not that beautiful. Usually they were doing galdring, and to galder means to really scream. You don't sing, you scream the words. Yeah? And I managed to get 350 people at this conference to scream together with me. I think maybe I can get you to scream with me. Can we do that? So this is the oldest rune markings we've seen. It's on a bone that was found just north of Lund. And someone has scribbled on this, well, carved into this bone of whatever it is. And if you translate it into somewhat later kind of runes, you get this. And if you pronounce it correctly, it says Ek, Erilar, Savilagar, Hataka. And you can translate it to English as well. It is I, the rune master, magic is my name. Talking basically about that it's some kind of magic that you can put words on bones and leave it for posterity. And it's magic. I mean, what we do is magic, right? We, the physics masters, understand it, but to everyone else, it's kind of magic. And the thing with galdring is that you take basically all syllables and all words, and you take them one at a time, and you stretch them. And I'm going to tell you approximately how to do it. I will take this off, not to destroy these things. So I will do. Need to use your stomach to get some power into it. But that is good. That is good for the digestion, for the lungs. So will you do this with me? Stand up. So we start just so we know the words. I mean, it's only 4 words, so you should be able to remember them. So it's Savilagar, Ateka. Okay, are you with me? I will make some lines. And stop. Thank you. So see you at 3 o'clock.